Okay, guys, so let us start our D and F block revision with the question: how many unpaired electrons are present in Mn2 plus ion, and how do they influence magnetic behavior of Mn2 plus? Yes, beta. So this is the question for you. Unpaired electrons in Mn2 plus. So just write down the electronic configuration. You know, manganese atomic number is 25 and its electronic configuration is argon 3d5 4s2. So Mn2 plus, electrons are removed from higher shell number, that is 3d5. Okay, so in this it is like this. Okay, okay, 3d5. So 5 electrons are there: 1 2 3 4 and 5, right? So number of unpaired electrons are 5. So how do they influence magnetic behavior of Mn2 plus? So as it has 5 unpaired electrons, it is highly paramagnetic in nature. It is highly paramagnetic in nature, right? Done. Next question number 2. So we are revising D and F block element through previous year questions from CBSE examination. Okay. No, this is question number 1. Now question number 2. There is a greater range of variable oxidation states. Oxidation states among the actinoids than among the lanthanoids. Yes. What is the reason? There is a greater range of variable oxidation states among the actinoids than among the lanthanoids. Why? So in actinoids there is a filling of 5F, 6D and 7S, right? So in actinoids there is a filling of 5F, 6D and 7S, and there is a less energy difference. There is less energy difference between these orbitals 5F, 6D and 7S as compared to 4F, 5D and 6S. Okay, in case of lanthanoids. Okay, that means more electrons are available for bonding in actinoids. Okay, more electrons are available for bonding in actinoids as compared to the lanthanoid family. That is the reason. Just write because of less energy difference between 5F, 6D and 7S as compared to 4F, 5D and 6S. In actinoids there is filling of 5F, 6D and 7S. In lanthanoids there is filling of 4f, 5d and 6s, and energy difference is less among these 5f, 6d and 7s. That's why more electrons are available for bonding in actinoids as compared to lanthanoids. That's it. Okay. Now question number 3. Question number 3 is, why is there a general increase in density of elements from titanium, that is Z22, to copper, that is Z29. Why is there a general increase in density of elements from titanium, that is Z22, to copper, that is Z29? Gradual increase in density. Why is it so? Yes, tell me. So, as we go along the period, see, this is the series titanium to copper. This is in the same period. So, along the series or along the period, atomic radii, there is a decrease. Generally, there is decrease in atomic radii as well as atomic volume. It gradually decreases. Gradually decreases, and at the same time, atomic mass increases. See, atomic volume or atomic radii decreases and atomic mass increases. That means density. And what is density? Mass by volume. So that likely to be increased. Okay, density is increased. Ashish, no, it is not because of 3D. In all cases, as we go along the series, atomic size decreases and atomic mass increases. That's why mass over size increases. That means density increases along the series. Okay, when we go from left to right, that is the proper reason. Okay. Now question number 4. So question number 4 is, say there occurs much more frequently metal-metal bonding. There occurs much more frequently metal-metal bonding in the compounds of heavy transition elements, that is 3D series. Okay, so assign a reason. So in transition elements, in transition elements there is NS and N minus D electrons, right, which are available for bonding. and these are generally unpaired, right? As a result, metal-metal bonding is quite frequent in these. Okay, that's why metals are lustrous, they are hard and have high melting and boiling point. Have high melting and boiling point. Okay, so what we write that in transition elements, a number of ns and n-1d electrons are available for bonding. Okay, since these are unpaired, and that's why metal-metal bonding is quite frequent in these. Okay, and because of that, they are lustrous, they are hard, they have high melting and boiling point. Or you can write there are a large number of unpaired electrons. Okay. Now question number 5. Why is copper 1 plus not stable in aqueous solution? Why is copper 1 plus ion not stable in aqueous solution? Or we can write, why is copper 1 plus is not known in aqueous solution? What are the questions? Why is copper 1 plus ion not stable in aqueous solution, and why is copper 1 plus is not known in aqueous solution? So copper 1 plus compounds, copper 1 compounds involving copper 1 plus ions are unstable in aqueous solution, and they undergo disproportionation. Like this. And why copper 2 plus is more stable? Copper 2 plus is more stable than copper 1 plus. Why is it so? It is because of high negative hydration enthalpy. High negative standard enthalpy of hydration of copper 1 plus copper 2 plus aqueous than copper 1 plus aqueous. Okay, and this, because of this high negative standard enthalpy of hydration of copper 1 plus than copper 2 plus, which is more than the, which will compensate the second ionization enthalpy of copper involved in the formation of copper 2 plus ion. Okay, beta. See, copper 1 plus disproportionate in aqueous solution. Why? Because enthalpy of hydration of copper 2 plus is more negative than that of copper 1 plus, which is more and which compensate the second ionization enthalpy of copper, which is involved in the formation of copper 2 plus. So what you should write? That stability of copper 2 plus ion as compared to copper 1 plus is due to more negative, high negative, or you can write more negative standard enthalpy of hydration of copper 2 plus aqueous than copper 1 plus aqueous, which compensates the second iron enthalpy of copper involved in the formation of copper 2 plus. This is the proper reason. Okay. So this is question number 5. Now question number 6. Lanthanum 3 plus, that is Z is 57, and lutetium 3 plus, that is Z equal to 71, do not show any color. In solution. Assign reason. So we have to assign the reason why lanthanum 3 plus and thank you, Ansh. Lanthanum 3 plus and lutetium 3 plus do not show any color in solution. So you know, it depends on the F orbitals. You know, in lanthanum 3 plus there is no F electron. It has configuration of, it is 4f0, and lutetium 3 plus, it is 4f14. So lanthanum 3 plus has no F electron and lutetium 3 plus has fully filled, completely filled orbitals. So there is no FF transition, or we can say there is no transition at all. That's why both of these ions do not show any color. Okay, beta. Why they do not show any color? Because lanthanum 3 plus and lutetium 3 plus, they do not have any unpaired F electron or partially filled F orbital. Okay, that's it. Now question number 7. Question number 7 is, explain why zinc is not regarded as transition element. Is not regarded as transition elements. Very good, Sajid. Explain why zinc is not regarded as transition element. What are transition elements? Transition elements are those which have partially filled d orbital in its, yes, in its ground state or in any of its oxidation state. They should have partially filled d orbital, but zinc has fully filled d orbital in its ground state as well as in its oxidation state. That's why zinc is not regarded as a transition element, because it does not fulfill the criteria of a transition element, which must have incompletely filled d orbitals in its ground state or in any of its oxidation states. So zinc has fully filled d orbital. It does not have partially filled d orbital in its ground state or in its oxidation state. Okay. Now question number 8. Okay, so explain why is cerium 4 plus ion a strong oxidizing agent. Beta, zinc, cadmium and mercury. Zinc, cadmium and mercury, they are not regarded as transition elements because of the same reason, that they have fully filled d orbital in their ground state as well as in any of their oxidation states. Okay, that's why zinc, cadmium and mercury are not regarded as transition elements. Okay. Okay, explain why is cerium 4 plus is a strong oxidizing agent. Cerium 4 plus, when gain 1 electron, we get cerium 3 plus. So cerium 4 plus is a strong oxidizing agent because plus 3 oxidation state is more stable than plus 4 oxidation state. Plus 3 oxidation state is more stable than that of plus 4 oxidation state. In all the lanthanoids, plus 3 is more stable than plus 4 or plus 2. This is the proper reason. Okay. Question number 9. Transition metals assign reasons. First, transition metals generally form colored compounds. And second, manganese exhibits highest oxidation state of plus 7 among the 3D series of transition elements. Yes, tell me. Say, actually all the lanthanoids we consider plus 3 as its highest, most stable oxidation state. Reason being, if more than 3 electrons are removed, energy required is very high, so that oxidation state becomes less stable. Okay. Transition metal generally form colored compounds. What was the reason? So transition metals generally form colored compounds due to DD transition because generally they have unpaired d electrons. Okay, manganese exhibits highest oxidation state of +4 among the 3D series because manganese has maximum number of unpaired electrons. It is 3d5 4s2, so it has highest oxidation state of +7 because there are 5 unpaired electrons, not vacant d orbital but incompletely filled, means exactly half filled configuration. Okay, so there are 1 electron in each d orbital. Okay, so due to the participation of n-1 d electrons and ns electrons, okay, they exhibit maximum oxidation state, highest oxidation state of +7 due to the participation of 2 ns and 5 n-1 d electrons. Okay, okay, question number 10.